All right, let's talk about quantum computing. We're going to separate the hype, the myth, from what's actually happening on the ground right now.
You hear it all the time, right? It's been called the next great technological revolution, something on par with the internet or AI. The big promise is that these machines will one day solve problems that are literally impossible for even the biggest supercomputers on the planet to crack.
But that really is the billion-dollar question. I mean, beyond all the headlines, what are these incredible machines really capable of today? To figure that out, we've got to first understand the dream, the vision that's pushing all of this forward. So, the quantum dream, it's really built on just a handful of absolutely world-changing algorithms. These are the theoretical keys that could unlock a whole new kind of computational power. Just take Shor's algorithm. It's the poster child for quantum supremacy. In theory, a big, powerful quantum computer running this could basically shatter the cryptographic foundations of our entire digital world. This is the kind of mythic, world-breaking power everyone talks about. But it's not the reality. At least not yet.
Okay, so if that's the dream, what's the reality for the researchers in the trenches every day? Well, welcome to what they call the NISQ era. NISQ. It stands for Noisy Intermediate Scale Quantum. And honestly, the name says it all. Noisy is the key word here. Think of it like you're trying to do some super complicated math, but your calculator is made of tiny, incredibly sensitive compasses, and the slightest breeze, or even just looking at them wrong, throws everything off. That's the noise. And intermediate scale? That just means you only have a handful of these wonky compasses to work with, not the millions you'd actually need. So this really lays out the massive gap we're looking at, right? On one hand, you have the dream, a perfect, fault-tolerant machine. On the other, today's reality. It's noisy, it's small, it's super prone to errors. Trying to run a monster algorithm like Shor's on a NISQ machine, that's kind of like trying to play a brand new 4K video game on a pocket calculator. It's just not going to happen. So how do we make any progress at all? So if you can't beat the noise, what do? You work with it. Researchers have come up with this really clever workaround. They call it the hybrid approach. And it's all about combining the best of both worlds. Okay, so here's the game plan. Your regular classical computer does all the boring prep work, right? It gets the data ready, sets up the problem. Then it hands off just the gnarliest, most quantum-y part of the calculation to the quantum processor. The quantum chip does its thing, spits out an answer, noise and all, and passes it right back. Then the classical computer takes that messy result, cleans it up, and uses it to figure out the next smart question to ask the quantum chip. It's this awesome little feedback loop. And look, this isn't just some idea on a whiteboard. This hybrid approach is already out there, being put to work on some really fascinating and genuinely useful problems. Let's check out a few. Take medicine, for instance. Researchers are using these hybrid models to help discover new drugs. Basically, they plug a special quantum program into their AI models to help them design brand new molecules from scratch. The quantum part is just way better at exploring all the insane possibilities of molecular structures. The hope is that it can find better drug candidates and do it a whole lot faster. And it's not just medicine. In finance, they're using these systems to create fake but super realistic market data. This lets companies test out trading strategies without messing with sensitive, real-world information. Over in healthcare, one project used a hybrid system to generate synthetic ECGs, heart signals. The AI they trained on this quantum-generated data got over 82% accuracy in diagnosing conditions. That's a huge deal for training better diagnostic tools. And one more. In material science, a hybrid model was used to create images of steel microstructures, and it actually beat the classical models in 70% of their tests. So you can see, even in this noisy, super early stage, we're seeing real, tangible progress. But all this progress has led to a really surprising discovery that's kind of changing how we think about quantum computing itself. Okay, so for decades, the quantum community had a pretty good idea of where the magic came from. But it turns out the story is a lot more subtle and honestly, way more interesting than we thought. So what is the secret sauce? What's the one thing that gives these quantum algorithms their unbelievable power? For the longest time, everyone pointed to this one thing, the Quantum Fourier Transform, or QFT. It's a key ingredient in so many famous algorithms, including the big one, Shor's. This was supposed to be it, the deeply quantum operation that classical computers just couldn't touch. But then, recent research dropped a bombshell. It turns out the QFT, this supposed heart of quantum power, has a kind of hidden simplicity. It has something called small entanglement. What that means is the quantum bits, the qubits, they aren't as deeply interconnected as everyone assumed. You can actually just trim away a lot of its complexity and it still works just fine.
And this is the kicker. If the QFT isn't as quantumly complex as we thought, then in many cases, a regular old classical computer can actually simulate it pretty well. I mean, this revelation totally turned the field on its head. Did it mean quantum computers were a bust? No, not at all. It just meant we were looking for the magic in the wrong place.
So if the secret isn't in the algorithm alone, where is it? Well, that leads us to a much clearer picture of what quantum advantage is really about.
Here's the new thinking. The power isn't just in the step-by-step recipe of the algorithm, it's in the ingredients you put into it. The real quantum trick, the thing a classical computer chokes on, is the input data itself, this incredibly complex, deeply entangled web of quantum information. So the true superpower of a quantum computer isn't just running a special set of instructions. It's the ability to create and then precisely control these unbelievably complex starting states of matter and energy. That is the task that is classically impossible. The algorithm, that's just the tool you use at the very end to pull a useful answer out of that incredible complexity. And understanding this new reality is totally shaping how the quantum future is being built. The focus now is all about creating practical tools that let developers and researchers actually get their hands on this true source of quantum power. And this isn't future stuff. It's happening right now, in software. You've got these two big players, PennyLane and Qiskit. Think of PennyLane as being laser-focused on quantum machine learning, perfect for building those hybrid models we were just talking about. Qiskit, which is backed by IBM, is more like a giant all-in-one framework for everything from chemistry to finance, and it's built to work perfectly with their own hardware. This is it. This is the real, tangible work of the quantum revolution happening today. So, look where we've come. We've gone from the myth of some all-powerful magic box to the reality of these noisy, specialized, but genuinely useful hybrid machines. We've learned the secret isn't just the algorithm, it's the incredibly complex data that you feed into it. The toolkits are here, and they're getting better every single day. Which leaves us with one last big question. Now that we know where the real power lies, what impossible problem should we solve first?